Hey everyone, I wanted to give you a little bit of a demo for this weekend. You have your discussion report due, and I want to go ahead and go through and give an example of how to process the data. What I did is I merged a couple of data sets together to make it a little bit easier to understand the data. So here what I'll do is I'll go through and show you how I would process the data from experiment 9. I will post a video later on experiment 8, and it's a little bit different, but I think for you to start writing your discussion, I think processing this data is kind of more important at this point. So the first thing I always do is I go ahead and I start working on the standard curve. And as you remember, the standard curve is it's A1 through 6, B1 through 6, and C1 through 6. So what I'm going to do here is I'm going to go ahead and take the means of those. But you notice there's overflows here. So in this case, this kind of tells me that for the standard curve, even if I put 3.9 in there, it probably is going to be off the line. So what I'm going to do is I'm going to ignore this point. Because I know it's not going to be my standard curve. It's not going to be in the linear range. So I'm going to start here, which means this is the 250 micromolar and so on. So I'll start down here is with the concentration of PNP and absorbance. Okay, so the top one is 250 micromolar, so I just put down as 250, and I'll go equals this divided by 2 equals, and I'll copy that down to here. I think it's as far as the curve goes. So the next thing is for the 250, I'll go ahead and take the mean of these three values. So go ahead and hit equals, type ARV, and highlight those 3 cells and hit enter, and then I'll take these down and do that like that. So here's the standard curve. Okay, so here's the standard curve. So what I'm going to do is I'm going to highlight these areas right here. I'm going to go to Insert, XY Scatter, and I'm going to put in a graph that looks like that with no line. And you'll see why in a minute. So we now have the graph here. And what I'll do here is I'll go ahead and click on that, right click on that, and I'll add a trend line. It'll pop up this menu up here. And what I'll do is I'll set display equation on chart, display R squared on chart. So I always like to look at my R squared to see how close they are. And this is 0.9996. This data set fits very, very well. So I randomly chose that from one student's data, and so someone did so extremely well. Okay. Now, what I also do, just because to determine the concentrations, I like to go ahead and calculate. And in the past, I've just gone ahead and taken those elements down, but I wanted to show you a new Excel function. And I'm going to type slope. And I'm going to type Y intercept. So that's equal to slope. Double click on slope, and we go back to this data set. The first part is known y's. So the known y's, let's go ahead and okay, I forgot. I did something wrong. What I did is I hid the data set, which I forgot that I was going to go back to it. So I'll have to just go ahead and delete. And I will move the data set down, the graph down a little bit. And maybe I'll type these X, and I'll put these over here now, really close to the numbers. So slope, I'll just go ahead and now start over, equals slope. It's the Y's, and then you hit a comma, and then you hit all the X's and hit enter. So there's the slope. You notice that 0, 1, 2, 3, 0, 1, 2, 3. And the intercept, I do the same thing, equals intercept. And what I'll do here is it wants the y values first, comma, the x values, enter. And 0.09, you see that that's 0.09, but let's go ahead and we'll add a couple more decimal places by going up here. You see 882, so it's got the same number. So we know that's the same number. So what I'll do is in calculating this, I will be able to refer to these cells now. So now we have a way to calculate the concentration of these samples. So what I'm going to do is I'm going to go through and look at the mutant data and go ahead and start generating some plots and graphs here. A lot of times what I'll do is I'll take each step along the way to do the graph. So here I'll go ahead and put substrate concentration. This will be wild type absorbance values. This will be mutant absorbance values. This is wild type concentration of a product, which is a measure of velocity. Mutant, same thing. So I'll have these set up this way. So what I'm going to do initially is I'm going to plot these data out this way. So we know the substrate concentration starts out at 20. And we know we go down here 10, 5, 1.25. So here's all our concentration substrates. Now we'll go ahead and do their mean absorbances here. So that's equal to average of these values right here and I can copy them down, and that's all those means. Now do the mutant is equal to average, and do the mutant now. What I want to do is determine the concentration, and you remember that the equation we fit into is y is equal to mx plus b. But if you want to solve in terms of x, go ahead and it's y minus b is equal to mx. So then we go ahead and put in terms of x is equal to concentrate the y values with the absorbance values minus the intercept divided by the slope. So remember that equation right here, and that's what I'm going to be using here to determine that calculation. So y is this value here, and m is this value here. So we'll start calculating that right now. It's equal to this value minus the y-intercept, and this y-intercept, we're going to keep that fixed in place, so I'm going to go ahead and put the dollar signs in now. Close the parentheses, divide it by the slope, and I'll go ahead and add dollar signs here. And dollar signs means it's no longer means it's a fixed cell that it goes back to. It'll go back, and you'll see why I'm doing that in a minute. So here, go ahead and go that down, and here I'll do the same thing again. Equals quantity y, which is this value, minus the intercept. I put dollar signs in to fix it in place. close it, divide it by the slope, and make that a fixed point in place. And we see here we've calculated them. Here, let's go ahead and that's too many decimal places. Let's go ahead and make it less decimal places. I think 1 decimal place is more than sufficient for this. So we see the value. So now we have the substrate concentrations, and now we have the velocities. So we had this much product produced over the length of time that you incubated the plate. If you want to, you can convert. We did about 20 minutes, so you could divide it by 20. I'm just going to go ahead and leave the values just the way they are. So we have this, and let's go ahead and plot this value. So here, highlight this value, hold the control, and go ahead and plot the wild type first. Insert, XY scatter, and I'm going to go ahead and draw lines here. And so here's what the lines look like. So this looks like a little bit of rectangular hyperbola. Maybe this value is a little bit low. And I noticed a number of the values throughout were these two values were a little different, and sometimes they were moved around a little bit. I'm not sure exactly what happened because it only happened for the wild type and not the mutant. So I'm kind of curious as to what happened here. Completely certain. So I'm going to go ahead and select data, hit this to select data up here. And what I'm going to do is I'm going to hit edit, and I'm going to type the name in. Type in wild type enzyme is the title of this one. Now I'm going to add some data, and that data, that's going to be mutant enzyme. Click right here. We'll take these values in. Make sure you only highlight the numbers in this case. And click here and highlight these numbers. And click there again. And click OK. And click OK. So you see we have two Kinetic plots. They look like they're very close to each other. I would go ahead and do some little beautification here. I'll go ahead and add a legend to the right. Maybe stretch it out a little bit here. Make it look a little bit nicer that way. And I will go ahead and add an element. Axis titles, horizontal. Type substrate. Use the brackets because it's a little bit easier. Oh. And that is in terms of micromolar. Okay. Now we'll go ahead and add the y-axis, the vertical. It's velocity, and that's actually micromolar, and actually the substrate is millimolar. So I made a mistake there. I will fix that. Nice thing about Excel is you can always fix these things. That's why I always keep these sheets around, and I will copy and paste out of them. But all my calculations I'll keep in a separate spreadsheet. So here we have a Michaelis-Menten plot. So this is one of the things that I wanted you to put in your report. And so here you have it in your report, and you'll be able to talk about this a little bit. Now, to be able to determine the kinetic constants, we don't, like here, you see this line here, it keeps going up. And so we don't really ever know what the Vmax is going to be here. I suspect maybe there's some kind of interesting kinetics here, but I'm not really sure what is happening here, but let's go ahead and let's go ahead and do the Langmuir-Burke plot. So the Langmuir-Burke plot, we need to have a column here, 1 over substrate concentration. So we do that. We have is equal to 1 divided by this. Hit there. We'll copy that on down. Now we'll have 1 over wild type, and I'll do the product again. And this will be 1/mutant. Let's go ahead and calculate these now. That is equal to 1 divided by this value. Hit enter. Copy those down. Then we do is equal to 1 divided by this value. Hit enter. And copy them down. So now we've calculated, now we have 1 over the substrate values and now 1 over the velocities for the 2 enzymes. So it's now time to go ahead and do our first graph. I'll just go ahead and highlight these numbers. And then right now, remember I'm doing wild type, and we'll go ahead and go to Insert, Charts, and I like these XY scatter plots. So do XY scatter, and we have the data points here. They don't look like perfectly on a line, but you see there's definitely a line. What I'll do here is right click on that, add trend line. In this case, I think I'll look, kind of my guess is we want to go ahead and project backwards a little bit. I need to go back a little bit more. .5 maybe. See, I'm doing this, I'm just kind of making it looking and just looking down here and seeing that want that line to cross the x-axis. So we now have, as we know that 1 over the velocity, what the y-intercept here is 1 over the velocity, and this x-intercept is -1 over the km. So we have those two values. Now we have it. What I like to do is I want to have a multiple equations here. I'm going to go ahead and I'm going to highlight this equation and I'm going to color it blue. Now I know the equation, the blue equation goes with the blue dots and the blue line. And that's something that I'll do frequently, particularly usually if it's just only 2 equations, I don't do this, but I think this is a good thing to try to do right here. So we now have the wild type enzyme present. So now let's go ahead and click on chart design. Go ahead and click select data. We'll go ahead and edit this. We'll go ahead and put wild type enzyme as the title of the series. So now it's wild type enzyme. Now let's add a data set. And we'll put mutant enzyme. We'll go ahead and put our X values, which is right here. And our so now we have 2 equations, the same horizontal axis, and now just click OK. Oops. What I did here, notice what I did here is I accidentally did not include all the data. So I'll do this. Now I have all those data points. So a lot of times if you go ahead and click on the data, it'll tell you what's in there, so you can correct and make corrections this way. So here I will go ahead and add trend line. Let's see, it looks like this one's going to go further out, so maybe 0.8 units. I don't need quite 8, maybe 7. It's like 7 touching the line there. Okay. Okay. Now what I'll do here is I'll right click on it, add trend line. That goes to, I think, probably about 0.7. That's 7, not 0.7. Display equation on chart, R square. Looks like it's hitting the line. It looks good. So let's go ahead and click on the chart here. Accept all that. And here the equation is there. What I'll do is I'll grab the equation and I'll move it down here. And like I did in the other one is I will highlight that equation. Go to home. And make it orange here. So now I have the equation. So now if I look at the equations, I'll know which one is which. And time to go ahead and make the graph look a little prettier. I'll click this X over here. So I'll take this graph here. Let's move it. Because you want to be able to have both of these graphs. Let's go ahead and do some readying this graph for your report. Let's go ahead and click Chart Design, click Element. Let's go ahead and put a legend on it to the right. What I do here is I don't like the trend lines to be labeled, so I just do this like that. We'll go ahead and stretch this out a little bit to make the graph look a little bit bigger. I like this right here, and I will edit this back here like that. There. Next, I find these lines here annoying, so I just click there and hit delete. Hit these lines, hit delete. Hit delete. Now you just have a nice clean graph. Now what we do here is let's go ahead and label our axes. So go to Chart Element and Data Axis Titles, Primary Horizontal. In this case, that's going to be 1 over substrate I'll probably want to go ahead and put millimolar here, and we need to put in our y-axis, axis titles, vertical, and we'll put 1/velocity. So now you have a graph that shows the equations, shows these plots, and you go and look here, you can actually see that it looks like that the Km here is probably, you can look here, the Km is probably a smaller number, remember it's a reciprocal, and here the velocities look like they're probably very, very, very similar velocities. So this mutant probably just changed the affinity to the substrate. So this is something that if you see an observation like that, you can make comments about that in your report. But how do you go ahead and how would you go about determining these numbers? Well, what I'll do here is I'll do a little calculation here for you. So now we have the graph. We have a nice graphic here you can put into your report. Now, what I want you to do, and I find that students have a few issues occasionally doing this, is to go ahead and determine what your intercepts are, and then you know that the Km is equal to, the Km is equal to the minus 1 over the Km is here, and minus 1 and 1 over the Vmax is here. So what we do is let's go ahead and determine our intercepts. So what I'm going to do here is have Vmax wild type, Km wild type, and I'm going to be calculating these. So I'm going to additionally do is calculate the intercepts. and then 1 over the intercept. And I will do the mutant the same way. And what I'll do is I'll do these in stages so you can kind of see what I'm doing. So I have 1 over the intercept and these values right here. So what I'm going to do here is the Km is when let's go ahead and do Vmax first. Vmax first here is Vmax is equal to the y-intercept. So that means that x is 0. So we'll go ahead and put an x of 0 in this equation. So then if you do is x is 0, so you've already calculated the intercept. So here, the wild type enzyme is right here. It's 0.0114 for the wild type. And for the mutant, it's 0.0115. So go ahead and do the reciprocals of those. It's equal to 1 divided by that value is equal to 1 divided by this value. And so we know the velocity here. The velocities are very, very similar. They're within 1% of each other. So they're probably, I would declare them as the same velocity, and that's what it kind of implies by it looks like it's crossing over at the axis. We know it's actually very close. Now let's go ahead and determine the x-intercept. Unfortunately, it would be nice if there was a nice Excel function to do it. I don't think there is an Excel function to determine x-intercepts. There is one for y-intercepts, but I figured I would just show you this way here. What we're doing is we see here we're going to make this 0. The y is going to be 0. So the x will be what we solve for, and here's the y-intercept. And so what we'll do here, and since I will go ahead and do the algebra, we'll move the 0.114 is equal to 0.022x. So it's actually going to be equal to 0.0114 divided by 0.022. And we know, since it's a minus sign, we know it's going to be minus. Let's just go ahead and not worry about the negative sign and hit enter. So we know the intercept is right around 5.18. And we look at the graph here, and that's probably about right. That looks right. So that's sort of, I look at there to get my sort of credibility. Does it look like I made the right calculation? Looks like I did. Now here, I'll go ahead and do the Km. Oh, these are mutants here, so I need to fix that. So here it's going to be the same thing. We're going to take the 0.115, move it to this side of the equation, and then divide it by the slope. So we'll go ahead and do that again. Actually, I probably could calculate this. Is equal to 0.0115 divided by the slope, which is 0.0174, correct? 174. Hit enter. So now we have that Km here, negative 66. Yeah, that looks like probably about right. Let's go ahead and then now go ahead and do the reciprocals. Is equal to 1 divided by this value. And here it's equal to 1 divided by, divided by this value. Enter. So we see that the slope here, the Km is about 1.5, so it's a little bit lower for the mutant. It's probably 25% lower. So that's probably a significant change. So we know that the affinity for the substrate has increased in this mutant. So this will be something you can write up in your discussion. So hopefully me going through these and showing you a little bit of labeling in Excel and all that will help you do your report. I will see you later. If you got any questions, feel free to send me an email. And if it gets complicated, we can talk about it over Zoom or we can talk about it in lab. I will see you later. Bye.